So far, we've seen that lines are very specific to elements, and that we can use these lines to infer some physical properties, such as temperature. And once we identify the lines and we know their wavelengths at rest frame or in the lab, what we'll be able to do is to measure any shift from the rest frame so that we can interpret it as a radial velocity. For this, we're going to use the Doppler effect, which I'm sure you're all familiar with, for example, both sound and light. And what the Doppler effect essentially tells us is that if an object is moving towards us, then the waves get compressed or blue shifted. They shift to higher frequency and lower wavelength. And if an object is moving away from you, then the waves get stretched and redshifted or to lower frequency. Now, the simplicity of the Doppler effect is that this change is only determined by the line of sight velocity v. And for most things that we'll cover in 263, we'll assume the non-relativistic case, and we'll be able to, by measuring shifts in wavelength when compared to rest frame, actually recover a velocity. It is important to understand, though, that the velocity that corresponds to that shift in wavelength is the projected velocity, the radial velocity, and therefore we'll need to either measure the orientation at which the object is moving, or we'll need to keep this theta angle or the angle in relation to face on, which is the angle I. It is important to understand the definition of the angles when we do some of the questions. You might be familiar with just using the angle theta, essentially away from a straight line from the observer. But in astronomy, we use this angle away from face on a lot. That's I. The only difference is that instead of using cos theta, we'll probably use sine I a lot. And this is the definition so that you understand how the angles are defined when we talk about it. Now, these shifts will be seen in, for example, the movements of stars. We'll be able to even use the movements of stars to discover and study exosolar planets, but they're also seen with huge values actually from galaxies. There are a few galaxies for which we can see blue shifted lines, such as Andromeda, because it is actually coming our way, but most galaxies actually have a significant redshift. And we'll see that the further away a galaxy is, typically, the higher the redshift. Combining spectroscopy with Doppler effect has a lot of applications in astronomy, as we'll see. There are some examples in your lecture notes, but as the course moves along, we'll actually encounter this again and again. This is how, for example, we determine the relative speed of stars and gas at a large range of distances, how we'll be able to measure essentially the velocity that the sun orbits the Milky Way, so we know how long it takes for the solar system to complete a full lap. This is how we can measure the masses of binary stars, for example, or even discover exosolar planets, as we shall see. As a quick practical example, let's consider the H2 region that's just behind me. Let's say that we take a spectrum of this H2 region that is shown here on the left. And a spectrum, remember, will be given in units of flux density. And in CGS, as I have used, that's erg per second per centimeter square per Armstrong. So let's say that you take the spectrum and it looks like this. So there's some sort of continuum, maybe there's a few stars, and also there's these three different emission lines. And when you compare with values from the lab, you realize that this line and also this line correspond to oxygen, and specifically doubly ionized oxygen, and also this line corresponds to H beta in the lab. But you also notice that actually in the lab they should be here, but you observe them at slightly shorter wavelengths, meaning all these lines are actually blue shifted. If they are blue shifted, what we can do is we can focus on one specific line, or we can even repeat this for different lines. But if you use Doppler effect, what we can infer is what is the likely, at least radial velocity. In this case, because it is blue shifted, the velocity is negative, and this means that this cloud specifically, if we were to take the spectrum, is actually coming our way at essentially 80.1 kilometers a second. This is a very simple example of how you can determine the dynamics, or essentially any relative speeds of different objects. Another example of application of the Doppler effect is when we combine it with Kepler's third law to determine masses of binary systems. You'll find all the details in the lecture notes, where you can also have a look at some of the most important steps that you need to take. Well, first of all, you could write down Kepler's third law for a system that's not just dominated by a single mass, so you have to include m1 and m2. We can also write that the average separation will essentially be given by the sum of the distance from mass 1 to the center of mass and mass 2 to the center of mass. Now, if we do that, we can also write that the average velocity for mass 1 will be given as 2 pi, the average separation of 1 over the periods, and the same thing for 2. And this allows us to write essentially this equation, that the average separation will depend on the periods and also the sum of both velocities. If we then use Kepler's third law, then we can actually write an expression for the sum of the masses that depends on the periods and the average velocities for both. And finally, we can actually we can determine how these velocities will depend on any shift of wavelength as the two stars complete the orbits. This is not super important. For now, we will come back to this when we study exosolar planets and also when we look at how we determine the masses of stars. Another really cool thing that we can do with the Doppler effect is, instead of just measuring the full radial velocity of an object, is actually to measure radial velocities on different locations within, say, a galaxy. In this case, what we're seeing is essentially data telling you that these two galaxies are rotating. We can see that towards this part of the galaxy, the light is being blue shifted, and towards this side of the galaxy is being redshifted. So what happens is this part of the galaxy is actually going away from us, and this part is going towards us, essentially in a disk that is rotating. And we can actually transform these observations very easily into some sort of rotation velocity. And you have one of these examples on the lecture notes and also as part of a question. So I would encourage you to attempt that. But in this case, it is relatively easy. You just look at the shift of wavelength, you compare it with what you expect in rest frame, you multiply by the speed of light, and you get the rotational velocity in terms of kilometers per second.